Hello everyone and welcome to QuantPy. We know how to derive the diffusion equation and we have seen its usefulness as well. This equation is the same equation as the heat equation, by the way. So you can see the same equation describes the dynamics of very different microscopic processes, diffusion of particles or heat transfer, and many other systems like chemical concentration. Now we're going to solve the equation. So we want to determine the function f subject to some initial conditions. We are going to use the similarity solution method. The method is very simple and very commonly used, but usually the details are hidden. So when you hear things like let's consider the following transformations and those transformations turn out to be the magic transformations, you know the similarity method has been used, most likely a software package. We are not going to discuss the general similarity solutions method, so we are going to stay glued to the diffusion equation and we are going to derive the equations heuristically using our understanding of the physical processes, and you will get the gist of the similarity solutions method under familiar circumstances, and then you can go and research the more general method. Right, so essentially the approach is all about finding transformation under which the equation is invariant and then using those transformations to reduce the order of a differential equation or the number of variables in a partial differential equation. In our case, we have two variables t and x, so we are hoping this method will help us reduce it to one variable, which we hope will be easy to solve. Let's see it in action. Before outlining the transformation under which this equation is invariant, let's quickly discuss some examples of elementary transformations. We have two variables t and x, so let's imagine we have two-dimensional grid and we have plotted t along the horizontal axis and the variables x along the vertical axis. Now the first transformation that one can consider is the humble horizontal translation. So essentially you add some constant a to the variable t, leaving the variable x unchanged. We shall see shortly how it looks geometrically. We can have its sibling, the vertical translation, in which we leave the t variable unchanged and shift the x variable by a constant. And you can combine the two transformations to shift the location of a point or collection of points. You can also consider magnifying the shape. So if you multiply a dimension by a positive constant, it will scale the coordinates of the point. The exponential is there because we want to restrict the multiplier to positive values. And for our final example, you can rotate the points by using the following transformations using sine and cosine. Looks complicated, but we shall see very shortly its geometric meaning is rather very simple. By the way, these are examples of one parameter group because we are using one parameter a, so this y is one parameter, and it's called a group because each of these transformations satisfy the properties of the theoretical construct, the group. You can also have more parameters. For example, a two-parameter group will apply different scaling to t and x. Now let's quickly see how these transformations look like visually. Let's say we plotted 4 points in two-dimensional grid. I have just joined them to create a shape. I should probably have added arrows as well to indicate direction. So you can try this if you like. So you see two panels. The second panel is essentially a clone of the first and is there to help see what happens to the point and the shape as we apply the various transformations. So I'll keep the first fixed and shift the second as I apply the transformations. Right, so first we try the vertical translation. So it just shifts the points vertically. So the shape is moving upward or downward, depending on whether the shift is positive or negative. Horizontal translation, as you would expect, means the point shifts along the horizontal axis. Let's see magnification now. It's also called perspective. Scaling the t variable by a factor greater than 1, well, elongate the shape horizontally. And let's see the magnification along the vertical axis. And if you use a scalar smaller than 1, then the shape shrinks in size. And the rotational transformations rotates the points, where the size of the rotations pretty much depends on the theta or a that we had in the sine and cosine. Now that we understand the transformations, let's go back to our diffusion equation. It's easy to see that this equation is invariant under horizontal and vertical translations. And slightly less obvious observation is that the equation is invariant under the following magnification. Here lambda is assumed to be greater than 0, and you can write it in terms of exponential as well, which is always positive, so the two forms are really the same thing. And the reason we are not considering the negative value is because multiplying t by -1 amounts to time reversal, which complicates things. As we have scaled the first axis by lambda and the second by lambda squared, so this transformation is also known as a parabolic scaling. Now to prove that the equation is invariant, we just need to apply the chain rule really. We explained this for the second transformation, and you can apply the same procedure to the first as an exercise. We can write the function f as a function of the new arguments. This is just a clone of the original function with the parameters renamed from t and x to u and v, so no transformation has been applied yet. So feeding the same two values to both functions will produce the same result. Now we need to link the two sets. U and v are functions of x and t, so we represent this clone of f as a function of x and t, the original variables with a tilde. This is because feeding the original x and t values get magnified before being fed into the function, so that's why we represent this function with a tilde to differentiate it from the original settings, and which the x and t are fed straight to the function. Now, to show that this tilde version of the function satisfies the PDE, we will need to calculate its derivative with respect to t and x. We will be using the chain rule, so let's first calculate the derivatives of the two transformations. They're just lambda and lambda squared. Now let's calculate the time derivative first. Simple application of chain rule. Now we just substitute for the derivative of u with respect to t that we computed earlier. Now for the derivative with respect to x, we apply the chain rule. Then substitute for the derivative of v with respect to x. We differentiate again because we need the second derivative with respect to x, because the heat equation has got the second derivative on the right hand side, right? So we apply the chain rule again and then substitute lambda again. So we get. Now we can write the diffusion equation in terms of u and v, the new variables. As mentioned before, this is just relabeling and no transformation has been applied. And now we can substitute for the derivatives with respect to t and x and to the clone version of the diffusion equation. So the lambda squared, or 1 over lambda squared to be precise, on both sides cancel. And now if we substitute for u and v, we see that the transform function satisfies the diffusion equation. Now for the next question, which is how do we find these transformations? The answer can be as long as you like. These are implemented in many software packages, but it's better to use heuristics. We know the scaling is one of the elementary transformations, so no rocket science there. The tricky part is probably the lambda and lambda squared, so let's see if we can come up with these. First thing though, if the function satisfies the diffusion equation, then a constant times f will also satisfy the equation because we have the function on both sides. Now let's see we apply different scaling to each variable, which we represent by b and c. So our v is equal to b times x and u is c times t. We hope to show that the function satisfies the diffusion if c equals b squared. We know what to do now, so we just differentiate with respect to t, which really amounts to the chain rule again, and it's easy to see that the derivative of u with respect to t is equal to c. Next, we need to calculate the second derivative with respect to x. We start with the first derivative, and the derivative of v with respect to x is obviously equal to b. We then differentiate again, and it's just essentially another application of the chain rule, and we know it will produce another b, so we get b squared. Now we write the diffusion equation in terms of u and v, then substitute for the two derivatives and the variables u and v. So now c must equal b squared if this were to have the same form as the diffusion equation. So if we set b equal to lambda, then c must equal lambda squared, and is the parabolic scaling demystified. Now we need to decide what value to use for a. It can be any scalar, but if you think about f in terms of the Brownian particles at a given time, then we know that its integral must equal the total number of suspended particles. So we can use this relationship to determine a. Let's transform the first variable, so set lambda times x equal to a new variable v. Its differential is easy to calculate. Making the substitutions into the integral, we get, and we can take the constant terms out of the integral. Now again we want the integral of the function to equal the total number of particles, which we can achieve by setting the constant term equal to 1. So a must equal lambda, and our function becomes. So we have found a setup transformation under which the equation is invariant, and now we are hoping it would help us reduce the number of variables by 1. If you set lambda equal to 1 divided by the square root of t, then this equation becomes. And now defining this ratio inside the function as a new variable, you can see we can transform the function into a function of one variable. But we want this function to be dimensionless so that it's independent of the system of units. We know the dimensions of x divided by square root of t is length divided by the square root of time. Remember, x represents the distance along the horizontal axis and t is time. So what's the best way to make it dimensionless? The answer is in the diffusion equation. Remember, when we approximated the derivatives by the finite difference, we had f in the numerator, which is the number of particles. So the dimension of the left-hand side is the change in particles per unit of time. So it's number of particles divided by time. And the right-hand side is a number of particles per unit of length squared. Rearranging, we see that the d has the dimensions of area divided by time, the square root of which has exactly the same dimension as our variable. So if we divide the variable by the square root of d, then the variable z will become dimensionless. Remember, d is a constant, so this is a function of just one variable z now. Now to determine the solution of the diffusion equation, we need to express the differential equations in terms of this function. We have seen this procedure twice before, so we just need to calculate the first derivative with respect to t and the second derivative with respect to x. For derivatives with respect to t, t now occurs in the function because z is a function of t and outside the function, so we apply the product rule. To calculate the derivative of the function f with respect to t, we just apply the chain rule. And the derivative of z with respect to t is easy. Now we can substitute these into the expression to get. By the way, the derivative of the last term with respect to t is the same as the derivative of z with respect to t without the x. Now we can factor out the common term. We also replaced x divided by square root of dt by z. Now we can calculate the derivative with respect to x, which is easy, just the chain rule. And the derivative of z with respect to x is trivial, so we differentiate again because we need the second derivative. Another application of chain rule produces another 1 divided by square root of dt term, so we get. Now we can plug these into the diffusion equation to get. Now we simplify the d and t terms on the right hand side, too many of them. Now the d and t terms on both sides cancel and we get, which we can rearrange to get. As this is now a function of just one variable z, we can change the partial derivative to total derivative. Now the last two terms really represent derivative of z times f, so we can rewrite it as follows. Now if we integrate once, the derivative reduces by 1 and we get the constant of integration. Essentially, if the derivative is 0, the expression must be equal to a constant because the derivative of a constant is 0, right? Now we know that f is an even function because remember we said a particle is equally likely to move to the left and to the right. It means its derivative at 0 must be 0, which implies the constant must be equal to 0 because the expression must be defined for all values of z, so it must be valid at z equal to 0. Now we can separate f on the left hand side. The derivative of log of f is equal to 1 divided by f, so the left hand side is just the differential of the log of f. We can easily integrate and then exponentiate to get. Remember, the log and exponential are inverse of each other, so they cancel each other. So this function is now giving the number of particles at z, which is roughly speaking distance scaled by the strength of the movements in the system. Remember, we defined d as the one-sided average of the squared displacements per unit of time. So d times t represents the total kind of strength of movements in the system. You can see the physical meaning behind the scaling and why it helps to make the problem dimensionless and simplifies so much. Now we need to determine f naught. As mentioned before, f naught is like the constant of integration and you determine the constant values using the initial conditions. Assume we dropped m particles at location x at time 0, where m is assumed to be very large so that the math and statistic rules apply. So we are assuming continuous calculus, right? It only works if you have substantially large number of particles and statistics relies on the laws of large numbers. As the total number of particles doesn't change over time, the integral of this expression on the right hand side must equal the total number of particles. Now to simplify the expression, we see that the integrand looks like the density of normal, whose integral we know. The total area under the normal is equal to 1, right? So let's transform this equation to get 2 in the denominator of the exponent, because remember the normal density is got minus 1 over 2 times x squared, which we can do by defining a new variable to be equal to the 1 divided by square root of 2 times z, the differential of which is easy to calculate. The upper and lower integration limits are infinity, so they don't change. Making the substitutions we get. Now the integral is the same as the total area under the normal distribution, but is missing the 1 over square root of 2 pi at the front, so its integral must equal square root of 2 times pi. And we can isolate f on the left hand side to get, and we can substitute back into the expression to get. Now we transform z back into x and t. Remember, the two functions were linked as follows, and z was defined as follows. So making the substitutions we get, and we can now expand the function f as per the solution at the top to get. Now let's see what we have done. So we pretended that we dropped a large number of particles at x equal to 0 at time 0. And now this expression is giving us the number of particles at location x at a later time t if the particles were moved as per the diffusion equation. Now our initial particles might have been distributed across x, but worry not, because we can now take another location and apply the very same logic to that location. We can continue this way to the third location and so on. So we can write the initial number of particles distributed across x as a function of x. We denote this by psi, so this psi of x at x equal to 0 will be equal to the number of particles m that we saw earlier, right? As there is a continuum of locations across x, we can aggregate across the locations by just using the integral representation. The x minus z just kind of readjusts the location of z to x, and the function psi represents the number of particles at location x, which is independent of time, right? Because we put the particles there at time 0. And this is the solution of the diffusion equation. So there are technical names for the terms that are appearing in this solution, which generalize really well. So the transformation probability, the x minus z squared business, is called the green function. And the initial number of particles, the psi function, is called the impulse. It's like you're providing an impulse at a location, and then this green function is telling you the response to the impulse, and then you aggregate it across the locations and you get the solution. Right, so I hope you enjoyed the video, and I look forward to seeing you in the next.